Hello everyone and welcome to part 3 of Congruences 1, in which we will investigate more applications of this great tool. Our first example will be casting out 9s, which is a quick way to give some assurance that a large computation has been done correctly without having to repeat the whole computation. For instance, let us take the computation 4027 times 45 is equal to 181,215, and we would like to know whether this computation is rather good or not, using of course our method casting out 9s. So how does this work? Actually, this will use the fact that on a clock of 9 hours, a number is congruent to the sum of its digits. Indeed, if you take a 4-digit number of the form a, b, c, and d, one can write it as a times 10 cubed plus b times 10 squared plus c times 10 plus d. For instance, if you take 9,425, which is a 4-digit number, one can write it as 9 times 10 cubed plus 4 times 10 squared plus 2 times 10 plus 5. But actually, we know that 10 is congruent to 1 modulo 9, which implies that 10 to the n is congruent to 1 to the n modulo 9, which is also the same thing as 1 modulo 9. From here, actually, we can deduce that 9,425 is congruent to 9 times 1 cubed, which is 9 times 1, plus 4 times 1 as well, which is 1 squared, because 10 squared modulo 9 is congruent to 1 from this property that you see here, and following the same fashion, we get plus 2 times 1 plus 5 modulo 9, which gives actually that 9,425 is congruent to 9 plus 4 plus 2 plus 5 modulo 9, which is the sum of its digits. And this is actually congruent to 20 modulo 9, which is also the same thing as 2 modulo 9. In the general case, one gets that ABCD is actually congruent to A plus B plus C plus D modulo 9, and this is because 10 cubed is 1, 10 squared is 1, 10 is 1, and 1 is 1 modulo 9. Because here it looks like d times 1. Here we can actually read that every power of 10 leaves 1 as a remainder on a division by 9, and those who are still skeptical about congruences, you can check this by hand, because for instance we have 10 squared is congruent to 100 modulo 9, and 100 we know it is congruent to 99 plus 1 modulo 9, and 99 is a multiple of 9, which means it is congruent to 0 modulo 9, and this is congruent to 1 modulo 9. If you go further, 10 cubed is actually 1000 modulo 9, and it is the same thing as 999 plus 1 modulo 9, and we know that 999 is a multiple of 9, so it is 0 on a clock of 9 hours, and this yields 1 modulo 9 as well. Let us now get back to our example, and we would like to know, let me remind you, whether this computation is rather true or not. So what we're going to do is to reduce everything modulo 9, and we know that 4027 times 45 is the same thing as 4 plus 0 plus 2 plus 7 modulo 9 all times 4 plus 5, and a straight computation yields that this is congruent to 13 times 9 modulo 9, and we easily see that this is congruent to 0 modulo 9 because 9 modulo 9 is 0. Now if this number here is also congruent to 0 modulo 9, one would expect that our computation is rather good. Indeed, we have that 181,215 is congruent to 1 plus 8 plus 1 plus 2 plus 1 plus 5 modulo 9, and this is congruent to 18 modulo 9, which is also 0 modulo 9 because 18 is a multiple of 9. Bingo! Let me remind you that doing multiplication modulo 9 was possible because we've shown in the previous lecture that multiplication is well defined modulo a clock of n hours. And by the same way, so is the addition here. Thus, my computation was probably right. Be careful, casting out 9s does not assert that the computation is correct, it rather says that there is a good probability that our computations were correct. To see this, let us suppose we have done the multiplication 12,527 times 35, and that we've got as a result 438,436. Reducing everything modulo 9, one finds that this computation is congruent to 1 plus 2 plus 5 plus 2 plus 7, all multiplied by 3 plus 5 modulo 9. This is congruent to 17 times 8 modulo 9, which is the same thing as 8 times 8 modulo 9, and this is because 17 is congruent to 8 modulo 9. And to compute this with a tricky way, this is actually congruent to 9 times 8 minus 8 modulo 9. This is because 8 times 8 is counting 8 times, and it is the same thing as counting 8 9 times and subtracting 1 time. I did this because actually 9 is congruent to 0 modulo 9, so this is all congruent to minus 8 modulo 9, which is the same thing as 9 minus 8 modulo 9, and this gives 1 modulo 9. On the other hand, 438 thousandths and 436 is congruent modulo 9 to 4 plus 3 plus 8 plus 4 again plus 3 plus 6 modulo 9 of course, and from here we see that 3 plus 6 is 9, so this is 0 modulo 9, and the remaining elements sum to 19 modulo 9, and 19 modulo 9 is actually the same thing as 1 modulo 9 because 19 is 2 times 9 plus 1 modulo 9, which is congruent to 1 modulo 9. So from here we see that both the computations give the same result modulo 9, one on both sides, but does this mean that our computation is correct? The answer is actually no, and I deliberately made the mistake to show you that casting out 9s doesn't really prove that equality holds. In other terms, this equality holds modulo 9, but this does not imply that this one holds as well. And in fact, we have that 12,527 times 35 is equal to 438,445. Let us now move on to a second application of congruences. It is very easy to recognize multiples of 2, for they always end with 0, 2, 4, 6, or 8. It is also easy to recognize a multiple of 5 because such a number ends with 0 or 5. But how can we recognize a multiple of 11? A number n is divisible by 11 if the alternating sum of its digits is divisible by 11. For instance, a number of 4 digits of the form a, b, c, d is divisible by 11 if and only if d minus c plus b minus a is divisible by 11, and this is what we mean by alternating sum because it alternates between the negative sign and the plus sign here. For instance, if you take n equals to 52,118, then the alternating sum is equal to 8 minus 1 plus 1 minus 2 plus 5, and we see here that we can cancel both of the ones here, and we get that our sum is equal to 11. Thus, the alternating sum is a multiple of 11, and from here one can conclude that our number n is itself a multiple of 11. Let us prove this with numbers of the form a, b, c, d. Indeed, we have that a, b, c, d is equal to a times 10 cubed plus b times 10 squared plus c times 10 plus d. But modulo 11, we know that 10 is congruent to minus 1 modulo 11, which yields that 10 to the j is congruent to minus 1 to the j modulo 11 again. And in particular, we get then 10 cubed is congruent to minus 1 cubed, which is minus 1 modulo 11. 10 squared is congruent to minus 1 squared, which is 1 modulo 11. And from here, we get that ABCD is congruent actually to a times minus 1, and this is because 10 cubed is minus 1 modulo 11, plus b times 1 because 10 squared is 1 modulo 11, plus c times minus 1 because 10 is minus 1 modulo 11, plus d modulo 11. Now if we rearrange this, one gets that this is congruent to d minus c plus b minus a modulo 11, which is the desired result. Now, before we move on, one last word about this criterion. Actually, they are very useful in divisibility because of their efficiency. So instead of dividing this number by 11, all we have to do is to compute the alternating sum of its digits, which is way lesser than the number itself, hence the efficiency. Congruences were first introduced by Carl Gauss in order to solve some polynomial equations in integers which we call Diophantine equations. Let us see how this works. We would like to show that the equation x squared minus 7y cubed equals to 3 does not have any integral solutions, which means that there does not exist any integers y and x such that x squared minus 7y cubed is equal to 3. Indeed, to solve this, one reduces the equation modulo 7, so if this is true for two integers x and y, it must be true on a clock of 7 hours, in which the equation becomes x squared minus 7y cubed is congruent to 3 modulo 7, but we know that 7 modulo 7 is 0, so the equation becomes x squared is congruent to 3 modulo 7. All we have to do now is to show that this is impossible. There is no integer squared that it is congruent to 3 modulo 7 actually. This is rather straightforward because we only have 7 cases to check. If x is congruent to 0 modulo 7, then we know that x squared is congruent to 0 squared modulo 7, which is 0 modulo 7, and this is different from 3 modulo 7. Now if x is congruent to 1 modulo 7, then x squared is also congruent to 1 modulo 7, and this is because 1 squared is the same thing as 1 modulo 7, and it is different from 3 modulo 7. If x is congruent now to 2 modulo 7, then x squared is congruent to 4 modulo 7, and 4 modulo 7 is also different from 3 modulo 7. If x is congruent to 3 modulo 7, then x squared is congruent to 9 modulo 7, but 9 modulo 7 is the same thing as 2 modulo 7, and this is still different from 3 modulo 7. If x is now congruent to 4 modulo 7, we know that x squared is congruent to 16 modulo 7, and 16 modulo 7 is the same thing as 2 modulo 7 as well. If x is congruent to 5 modulo 7, then x squared is 25 modulo 7, and 25 is the same thing as 4 modulo 7, which is different from 3. And finally, if x is congruent to 6 hours modulo 7, then we get that x squared is congruent to 36 modulo 7, and 36 modulo 7 is the same thing as 1 modulo 7, because 36 is 1 plus 35, and 35 is a multiple of 7. Bingo! So we see here that x squared cannot be congruent to 3 modulo 7, from which we deduce that this equation is impossible, and so is this equation. Before we end our lecture, let us try our tool one more time on a very important equation. In fact, if p is a prime number, then it is either of the form 4n plus 1 or of the form 4n plus 3. And now I'll let you figure out why. In this example, we will show that if p is of the form 4n plus 3, then the equation x squared plus y squared equals to p has no integral solutions, which means that p cannot be the sum of two integral squares. Now I hope you figure out what to do, because it is all about reducing modulo 4, so if p is of this form, we get that p is congruent to 3 modulo 4, which is that if x squared plus y squared is equal to p, then we must have that x squared plus y squared is congruent to 3 modulo 4, which is an impossible equation, and I'll leave it to you to see why. We will investigate this equation more in depth in future lectures, and we will see why it is very important, and especially well studied by His Excellence Fermat. Congruences 1 Part 3 ends here, and believe me, our great tool Congruences did not deliver all its secrets, which we will investigate in future lectures. Thank you for listening.